guys. So I'm gonna try to figure out where I can stand so I can be on the frame. Okay, never mind. So, all right, as promised, I am making you a video of some problems. I'm gonna go ahead and work through 7 and 8 and 9 on the first page, and then we'll go and look at some of the other chain rules. And this is all trig derivatives, but first with some just sort of trig derivatives mixed into other formulas, and then trig derivatives inside of chain rule. Okay, so I did tell you that we probably weren't going to see cosecant very often, but if we flip back to the notes, which I can't do very well, so I'm going to try. If I flip back, all right, we've got our cosecant derivative is negative cosecant cotangent. It's one of the two derivatives that show up as a product of two functions, and it feels really random to have the derivative of the cosecant have a cosecant in there, but then also have that cotangent, sort of the same way the secant has a secant and a tangent. So we've got, back to this guy, whoops. Yeah, still a lot of whoops. There we go. See if this will work. Okay, so we've got our cosecant. We've also got a polynomial term. We're adding the two together. So when we take the derivative, we're just going to take the derivative of each piece separately. So my derivative is 20x cubed plus negative cosecant 3x cotangent 3x times 3. The 3x is like the u in the formula. So when we write the derivative of the cosecant of u, we have negative cosecant of the u, cotangent of the u, and then derivative of u. So yeah, pretty messy answer. 20x cubed minus, I decided that started with an S, minus cosecant 3x. Oh, good to see I do the exact same stuff. Okay, cosecant 3x. But actually, let me move that 3 up front. That's what it's hard to be me sometimes. Oh, good grief, Charlie Brown. There we go. I don't know what's going on in my life here. Here we go. Okay. Now we're going to have a green pen. All right, but we'll live with it. Minus 3 cosecant 3x cotangent 3x. Boom. Okay. Next, making sure I'm looking at the notation on this. It's a secant. It's supposed to have everything under the root. It doesn't quite look like that, so it should be, I think we're looking at the secant of the root of 2x plus 1. So as we go to write that derivative, the secant, again, has this derivative that's a product. It's a secant times a tangent. So if we're looking at, right here, so I'll have a little bit more room. The secant of the square root of 2x plus 1, u is the square root of 2x plus 1. So du that we're going to need is going to be a chain rule part. It's going to be 1/2 2x plus 1. So the negative 1/2 times another 2, which if I would like to simplify that, that can be 2x, just 2x plus 1 to the negative 1/2, because that and that will multiply to 1. This won't let me do anything else. Oh, it is. Okay. So knowing that, the derivative of the secant of u is the secant of u times the tangent of u times the derivative of u. So it's going to be the secant of the square root of 2x plus 1 times the tangent of the square root of 2x plus 1 times, move this guy over the way so I can see a little bit, times 2x plus 1 to the negative 1/2. So this could be made really looking crazy. Secant of square root of 2x plus 1, tangent of square root of 2x plus 1, all divided by the square root of 2x plus 1. And as tempting as it is for you to look at all those 2x plus 1 roots and go, ooh, divide, 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 nothing cancels out. This is its own thing that belongs to the secant. You can't take it away. You can't take this away. So this guy being the same as those two doesn't give us any advantages for simplifying. Nothing we can do. All right. So there's number 8. And then number 9, myself out of the way here, we've got the quotient rule. And inside the quotient rule, we've got a product rule in the numerator part. So we are going to have to do a quotient rule. Let's see, this is going to let me do my screen grabby thing. Yeah, I think it will. There we go. Hopefully send it to another. No, do something else. Where did it go? Come on. Oh, there it is. I see it hiding on this page somewhere. Oh, there it is. I see you. There we are. Okay. So here we go. We're going to quotient rule this thing. The f, the numerator, is 2x sine x. So when I f prime, I'm going to have to hit it with a product rule, which means I'm going to have to think about this guy also breaking it down as a 2x times a sine x. So when I build my f prime, I'll have sine x times 2 plus 2x times cosine x. Now, luckily, despite the fact that the numerator was kind of a hot mess because it's got a product rule inside of it, the denominator is pretty simple. My g is x plus 1, g prime is 1. So we've got at least that going for us. So I've got a pretty complicated f prime. So when I start creating my derivative, g f prime minus f g prime over g squared, it's that first part that's going to be really kind of ugly. My g is basic, x plus 1. My f prime is a sum. It's the 2 sine x, I'm going to move that 2 out front, plus 2x cosine x. That is just g times f prime minus, I do love being able to move this stuff around because it does get messy, minus g, oh no, g f prime f comes next. So f is what was up there in that product, 2x sine x. Ooh. 2x sine x times g prime of 1 over x plus 1 quantity squared. Crazy looking, for sure. Once again, very tempting. Nope, can't take anything out because you don't have an x plus 1 back here. You're always going to see a match right there. You're always going to see that in a quotient rule, and it never lets you take something away. It's very rare that you'll have a matching term back here as well. Okay, so those are the three to finish up page 3. If we flip into page 4, I'm not going to do all of these, but we can do a couple of them. The main thing that's going on page 4 is the fact that we've got the trig function expression being raised to a power. Okay? Or that's at least what's happening on the first 4. We also have a couple places where we've got the trig function. Oh, we've only got that one place, the trig function of a trig function. So in all of these cases, I've got an inside. If I rewrote these using the notation a little differently, you see I've got an inside that has trig. I've got an f of g of x, where the g of x part is the trig part. And I think we looked at this one last time, but it's worth doing again. I start taking the derivative of f, and the derivative of f, because f appears to be just an x squared function. When I take the derivative of that, it's going to be 2 times what's in place of the x. And what's in place of the x is sine 4x. Because the derivative of, if f is x squared, then my derivative is 2x. So I've got 2g of x times the derivative of g, which is going to be cosine of 4x. And because when I take the derivative of sine 4x, that hits a chain rule for the argument, sine 4x, cosine 4x, 4. And so we went ahead and put that together as 8 times the sine of 4x times the cosine of 4x. So maybe we'll pick a couple of these that we haven't done yet. Maybe let's do 14, and let's do 15. Actually, well, 13 and 15 are very similar. So let's do 14, let's do 15. Let's go through and we'll just do some rewriting on these. And if you want to go back and do number 11 after we do 15, 11 and 13 are very similar. 12 is going to be very similar to 10. Having the root there, like we have on 15 and 11 and 13, having something under the root, I think that's easier to remember to do chain rule. Because when I see that root, it sort of automatically slows me down and go, oh yeah, I got a big old thing to a power. So I'm going to run the power rule around my tangent 2x. And then because my tangent 2x is my g, I need a g prime. Derivative of tangent is secant squared of u times the derivative of u. Remember, the nice thing about a video is that you can always stop it and roll back to look and see what we did. Simplifying this, I'm going to come over here just to give myself some room. If I look at what all that looks like, it's a 1/2, it's a tangent 2x to the negative 1/2, it's a secant squared of 2x, and it's a 2. The 1/2 times the 2 will divide out. The negative root means we can throw that in the denominator. So it's going to be a denominator of the square root of tangent of 2x and a numerator of a secant squared of 2x. Try 13 and try 11. They're going to work similarly. You're going to write, when you think about 13, you're going to think about the cosine of x squared all to the 1/2 power. The cosine of x squared is your g. Here, 5 sine 2x to the 1/2 power. The 5 sine 2x is your g. On 12, if you rewrite this as the cosine of the quantity 2x plus 1 and then a big old cube on the outside, then you can attack it very similarly to your roots. You've just got this whole expression as your g. There's going to be a key for you to check answers. So as you're working on this after your quiz, you can go in and check answers. Let's go ahead and look at 14. And then I'm going to give you a little bit on 19, and then we should be good to go. All right, so let's take a look at 14. It's the sine of the cosine of x. So in trig language, u is the cosine of x. And I have the sine of u, which the derivative is going to be the cosine of u times the derivative of u. If u is the cosine of x, then the derivative of u is negative sine x, technically times another one. So when I put these pieces together, I'm going to have the cosine of the negative sine of x times 1. That's actually not too bad. If you can just kind of look at these and just say, okay, let me just focus this on as a u. Separate it out, rewrite it, because when you see it this way, it's real easy to write it this, and then you go, oh, let me now just fill in the blanks. What was u? Oh, I totally messed that up. Except I did that all wrong. Oh, I'm so glad that's on tape too. And you can tell how old I am because I call it tape. Okay, try that again. Sine of u is cosine of u. If u is cosine of x, oh, check this out. This is really going to look weird. Cosine, I thought that didn't look right. Cosine of the cosine of x times negative sine x times 1. There we go. Oh my God, that's crazy looking. It's the cosine of a cosine times a negative sine. It's so easy to get the pieces and parts mixed up. That's why using the substitution trick, writing it in its substitution form, and then plugging things back in, a lot of times helps keep you honest. All right, so like I said, if you go through the rest of the problems on this page, you should be able to go in and check some answers. Number 20 and number 21. Number 20 is just write a derivative. Number 21 is find the derivative value at pi over 3. So nothing super special about these. 19 asks for a tangent line and a normal line. Okay, so this is new. Tangent line. The slope of the tangent line is derivative value. My point is pi over 4, 1. So I want the derivative value at pi over 4, 1. But most derivatives, at least the ones we're working with, are only written in terms of x. So the 1 isn't really going to be super important for the derivative part. I keep doing that. Let's try that again. I'm going to put my ordered pair on there. Okay. So let's check out the function. Y equals root 2 times the cosine of x. My derivative will be root 2 times negative sine x times 1, derivative of x. Just chain rule that. So at pi over 4, that's root 2 times negative sine of pi over 4. So that's root 2 times negative root 2 over 2. That's sine of pi over 4. Which is going to turn out to be negative 1. That is going to be my slope. They gave me a point. I don't even have to do any extra thinking about the point. So my tangent line, if I use my point slope form, my tangent line would be y minus 1 equals negative 1 times quantity x minus pi over 4. Because remember, if you look back at the problem, they gave us the point pi over 4 1. So that would be the tangent line. Now, you're freaking out because they're like, but I want this other line. Well, if you find the tangent line, the normal line is super easy. It's like almost like buy one, get one free. A normal line is just the line that's perpendicular to the tangent line. Gent. Oh, I wrote that as like, sometimes I'm weird. Actually, all the time I'm weird. There we go. Perpendicular to the tangent line. Give me my pen back. There we go. Tangent line. So this is a geometry question. Lines that are perpendicular have slopes that are opposites and reciprocals. Which is a little bit more exciting when you have a number that's not a 1, because 1 is its own reciprocal. So my normal line equation is going to use the exact same point, pi over 4 1. It just needs to use a different slope, an opposite reciprocal slope, which means positive 1. Just a quick reminder, opposite reciprocals. For example, if I had a slope of 5/2 for the tangent line, my slope for the normal line would be negative 2/5. Right. So anytime you get a tangent line, you can write a normal line too. Okay, so that's a little bit of stuff for you to use to help you work through the rest of your lesson 9 notes. And hopefully that'll help you. Thank you.